Maximum likelihood. So probability distributions are vectors in the following sense. If we have a variable y associated with a set S of R outcomes, a list of numbers P1 to PR is a probability distribution on S if they sum to 1 and are non-negative. Correspondingly, the positive cone of R to the R is the set of vectors with non-negative coefficients. For example, the positive cone of R2 is the first quadrant of the xy plane. The positive cone of R3 is the first octant of XYZ space. The L1 norm of a vector is the sum of the absolute values of its coefficients. So the probability distribution space, the set of all probability distributions on a sample space of size R, is thus defined. Now, if a variable has a probability distribution, then we can sample that variable using its probability distribution. But first, we need an algorithm that uniformly randomly generates numbers in the unit interval. So a uniform random number generator, well, it's a generator, which means it takes no arguments, but instead produces returns using only its internal state variables. Random means every call of the random number generator is independent of every previous call and also independent of the ordering of the unit interval. Uniform, the probability of u being in a call of u being in a plus t, b plus t is b minus a for all t and r. So in other words, as we slide along, we still keep the same probability as long as a plus t, b plus t is in the unit interval. So we can use this to talk about sampling a random variable. So we've got y associated with S, R outcomes, and some probability distribution P in PDR. This V here is a vector space. It doesn't matter which one, but right now R to the N or the grayscale image space. Inverse transform sampling is where you partition the interval 0, 1 into subintervals of length P1 to PR respectively. Then you generate M calls of U, labeled U1 to UM. These are M trials. If U sub j is in the interval corresponding to P sub y, then trial j has value T sub y. For example, if we run our uniform random number generator, then it generates with the probability distribution P a set of trials. We call this sampling with replacement. The independence of calls of U means each trial has the same probability P sub y of producing outcome T sub y. So we're going to find variables y sub j associated with S, whose value is the outcome in S produced by the j step of inverse transform sampling. That means y1 to ym, capital Y1 to ym, is associated with S. They all have the same P. They're identically distributed. Also, variables capital Y sub I and capital Y sub j are independent because for all I and j, where I is not equal to j, the probability that y is t sub k, given that y sub j is t sub l, is just the probability that y sub I is t sub k for all k and l and 1 to r. We say that y1 to ym is a set of m identically and independently distributed IID trials of y, sampled with replacement, in other words. Suppose we were given data where the y sub i's are in S for all I equals 1 to m. Well, then define variables capital Y to capital M so that they're identically and independently distributed trials of y associated with S, and suppose that y sub I is the outcome little y sub I in the data set for all I equals 1 to m. Then that means some probability distribution P produced y1 to ym via inverse transform sampling. If we can find that probability distribution, not only will we have what generated the old data, but then we can also sample it to produce new data. So to do so, let's look at joint probability for independent trials. So we've got capital Y1 to ym. These are independent trials of y associated with S. And little y1 to ym is our data set, the values of capital Y1 to ym. Now, if the trials are sampled with probability distribution P in PDR, then that means we can think of these values coming from inverse transform sampling. But if they came from inverse transform sampling, then the joint probability distribution, given that these trials are independent, is just the products of the individual probabilities. In other words, we just have these probabilities. Now, we can reorder. So if we let M1 be the number of trials with value T1 and M2 the number of trials with value T2 and so on and so forth, then we see we would get P1 M1 times and P2 M2 times and PR MR times. Or in other words, we would have P1 to the M1 times P2 to the M2 times PR to the MR. That is, our joint probability, these are independent trials, is equal to the product of these probability coefficients of P to the M powers respectively. For example, suppose we had 100 trials of a coin with 20 tails and 80 heads. Well, M would be 100 and M naught would be 20 and M1 would be 80. And the joint probability would be the probability of tails to the 20th, the probability of heads to the 80th. For a fair coin, this would be a half to the 20th, a half to the 80th, or a half to the 100 power. For a biased coin, it would be tails now has a probability of 0.4, so 0.4 to the 20th, 0.6 to the 80th. So here's our problem. Given data, we do not know which probability distribution was sampled to produce our trials. So our goal is to determine which probability distribution most likely produced these trials via inverse transform sampling. That is, what partition of the unit interval was most likely to give us our data. Here's our joint probability distribution, but we're going to define a function on PDR, the set of all probability distributions. So this is the joint probability distribution because the trials are independent. And we're going to call this our likelihood function. In other words, our likelihood function from PDR to R is defined. L of P is the joint probability that capital Y1 is little y1, the first value in our data set, all the way out to capital YM is little ym, the last value in our data set. Now, if we have independence, which we do, then our likelihood function looks like this. And notice these all add up to M. That's the number of trials. So in general, the probability of an event as a function of possible probability distributions is the likelihood function for that event. So that takes us to the maximum likelihood principle. Now we're going to assume only strictly positive probabilities and that every outcome in S occurs at least once in our M trials. This is to avoid probabilities of zero because they do not contribute to the production of trials. The maximum likelihood principle is that the likelihood function, L of P, is the joint probability that capital Y1 is little y1, so on and so forth. It's a function of P. It's a mapping from PDR to R. And the maximum likelihood model for Y is the one that maximizes the likelihood function over PDR. So we saw that our likelihood function looked like this. And notice that the logarithm of AB is the log A plus log B, so we can apply the logarithm throughout, and that product turns into a sum. And then the powers turn into coefficients, given the properties of the logarithm. And so we have our sum, I equals 1 to R, M sub I log P sub I. Now the natural log is increasing, so the argmax of the likelihood function is the same as the argmax of the log of the likelihood function. So our maximum likelihood principle problem is to maximize the log likelihood subject to the probabilities summing to 1. In other words, the sum I equals 1 to R, M sub I log P sub I, subject to the sum of the P's minus 1 being 0. So here's why we like log likelihood. Suppose we have 100 trials of a coin with 20 tails and 80 heads. Our joint probability looks like this, and therefore our likelihood function of P sub T P sub H is P sub T to the 20th, P sub H to the 80th. For a fair coin, that would be the likelihood of 1/2, 1/2, which would be 1/2 to the 100, which would look like that, 30 zeros. For a biased coin, probability of tails of 0.4, our likelihood would be like this, which is 25 zeros, and that gives us this number. And we humans are just not comfortable working with these kinds of numbers. So what about log likelihood? Well, we have our likelihood function. So our log likelihood function is 20 log p sub t plus 80 log p sub h. For a fair coin, our log likelihood is 20 log a half plus 80 log a half is negative 69.31. For a biased coin with probability of tails of 0.4 and heads 0.6, we get a log likelihood of negative 59.19. And notice that these are numbers we're comfortable with. For probability of tails of 0.2 and heads of 0.8, negative 50.04, negative 54.48. And so among these, the maximum is the negative 50.04. That's the maximum log likelihood. It's not the maximum likelihood, it's logarithm of it. But notice we get the same argmax, 0.2, 0.8 for both. So we can find the maximum likelihood distribution directly from log likelihood. Let p equal p sub h, and so p sub t is 1 minus p. Our log likelihood function is therefore 20 log 1 minus p plus 80 log p. Define a function f of p as 20 log 1 minus p plus 80 log p. Take its derivative, take its second derivative. Second derivative is negative, so therefore we're going to have a maximum at p star where f prime of p star is equal to 0. So 20 over 1 minus p star is 80 over p star. Do a little bit of algebra, a little bit of rearranging. We get 100 p star is 80. P star is probability of heads, which is 0.8. Probability of tails, 0.2. So the maximum likelihood principle applied to log likelihood is an optimization problem whose solution is the data's maximum likelihood distribution, p star. In other words, the one most likely to produce the data via inverse transform sampling. So in order to do these kinds of optimization problems, let's start with some convexity preliminaries. Set C, a subset of a vector space, is convex if P and Q in C implies 1 minus alpha P plus alpha Q is in C for all alpha in 0, 1. In other words, the line segment within points P and Q is in C if P and Q are in C. A function is convex if its epigraph is convex, the epigraph being what's above its graph. So if the graph of f and the region above it form a set that contains all the line segments between its points, in other words, it's convex, then we say that the function is convex. And there's a theorem. If f from R into R is convex and there is an x star such that the gradient of f of x star is 0, then f of x star is less than or equal to f of x for all x in Rn. And we call this x star the argmin of f. So some calculus preliminaries. If x star is an argmin of f and g is increasing, then x star is also an argmin of g composed with f. The proof is quite simple. I'll let you take a look at it here. For example, if f of x is x transpose x, that's convex and has an argmin at 0. And g of x equal e to the x is increasing, so therefore e to the x transpose x also has an argmin at 0. If f is convex, then negative f is concave, and similar ideas apply. The argmax of a concave g is the argmin of the convex negative g. Composition changes the values of the extrema, but not the location, not their argmin or argmax. So some optimization preliminaries. A convex equality constraint, a convex function required to satisfy c of x equals 0. If we have a convex f and convex constraints, then a convex optimization problem with k constraints is as follows. Find an argmin of an objective that is subject to the constraints. Notice the asterisk can be either a superscript or a subscript. The Lagrangian of a convex optimization problem is a function of x and these lambdas where we have f plus the linear combination of the constraints. We have a theorem that says if the gradient of the Lagrangian at x star is 0, then x star is the argmin for our convex optimization problem. So let's look again at log likelihood models. So we're going to do this problem where there are no other constraints, no assumptions, and no parameters. So the Lagrangian looks like this. We take the derivative, the gradient, set it equal to 0. That means the derivative with respect to each p sub I is equal to 0. So m sub I over p sub I star minus lambda is 0. P sub I star is m sub I over lambda. The sum of the p's has to be 1, so the sum of the m1 over lambda up to mr over lambda has to be 1. So we have m trials over lambda is 1. Lambda is equal to m. P sub I star is m sub I over m. So our solution, our argmax for our log likelihood problem, is P sub I star is m sub I over m. And this is what's known as a relative frequency, the count as a ratio of the total. And we often call this an empirical distribution and denote it using P tilde. And notice it's also in PDR. But often our goal is the best probability distribution from a family of probability models with parameters. So this is our second example. We have these parameters, and we want to find the values of the parameters that yield the maximum likelihood distribution for that family. So we're going to look at the example of an unfair spinner spun independently 1,000 times, and we know that the probabilities p sub I are of the form e to the beta naught plus beta 1I. Notice there are 4 outcomes. So we're looking for which probabilities gave us this unfair spinner. So our maximum likelihood problem is to maximize over the parameters where m sub I is the number of outcomes equal to I, the number of spins that ended in the ith location of our spinner. Notice we have e to the beta naught plus beta 1I, so when we take the logarithm of p, we get beta naught plus beta 1I, and then we just replace the p sub I in the constraint by e to the beta naught plus beta 1I. We can factor out the e to the beta naught, and here is our data. So we want to solve this. So we need our Lagrangian, which is this function of beta naught, beta 1, and our lambda. We take its derivative with respect to beta naught. You can see that we simply get the sum of the m sub i's, and that's 1,000. You just add them up. And then the derivative with respect to beta 1 is the sum of the m sub i's times I plus that lambda term. And that's 2,550. And so the derivatives are equal to 0 when we get these two conditions satisfied, but we can take the fractions of those, and that means we can cancel out the negative lambda e to the beta naught, and we end up with simply this fraction equals that fraction. Or in other words, e to the beta 1 plus 2e to the 2 beta 1 plus 3e to the 3 beta 1 over 1 plus e to the beta 1 plus 2e to the 2 beta 1 plus e to the 3 beta 1 is equal to 2.55. You can solve that. It's actually e to the beta 1 equals 3, or beta 1 equals the natural log of 3. Now we can plug that back in. So beta 1 and e to the beta 1 is 3, so that's 3 to the I in the sum, but that can just be added up. It's 40, and e to the beta naught's 1 over 40. So beta naught's negative log 40. So our maximum likelihood distribution is e to the beta naught plus beta 1I, e to the negative log 40 plus I log 3. Or we could write it in this way, and that would give us 1 over 40, 3 to the I. So p to the I is 3 to the I over 40. P naught is 3 naught over 40. P1 is 3 to the first over 40. And now accordingly, P2 and P3. So maximum likelihood models, often this maximum likelihood principle is justified. We often can assume we have independent trials, and often the best model is the probability distribution that is most likely to produce those trials. It's flexible and pragmatic, converts finding a best probability distribution into a straightforward calculus problem. Many applications and many extensions. But one big drawback, we tend to have to assume a family with parameters, and that can be limiting.